Alright guys, so today we're going to start talking about thermochemistry. Overall, looking at some important vocab and concepts from Chem 1 with Thermochem, and then we're kind of going to branch out throughout the rest of the unit and go over some other things. Thermochemistry is really going to focus on the relationships between chemistry and energy. Particularly whenever you are making bonds, breaking bonds, how it changes, how heat changes over a reaction, what happens to the actual particles as energy is added to a substance. And we're going to look at how these changes accompany any change in matter. All right, some important vocab to remember. Energy is the ability to do work or supply heat. More specifically, we're going to talk in regards to energy, we're going to talk about work and heat. Work is a force acting over a distance. So kind of being able to create a change in that reaction. Whereas heat, we're going to talk about a little bit more. This is the flow of energy caused by a difference in temperature. So the energy actually going from one object into another. I want you to think of energy as a quantity that an object can possess, or a group of objects can possess. So actually how many joules they're gaining, or how much energy specifically they're gaining. And this could be a single particle, or it could be an object as a whole. Whereas we're going to think about heat and work as two different ways that an object is exchanging energy with other objects. So energy is the quantity itself. Heat and work is going to be the exchange of that energy. All right, so there's a couple different types of energy that you need to be aware of. A big one that we've talked about in Chem 1 is kinetic energy. Remember, this is energy due to motion. This was kind of related to why we have temperatures and stuff. Whereas we most specifically in Chem, we talk about thermal energy. It's still under kinetic, but we talk about thermal associated with temperatures. That's where we talked about the faster the particles are moving, it can change its state of matter. Or the hotter something is, the faster the particles are going. Some that you may not be as familiar with are potential energy and chemical energy. Potential energy is energy that is stored for later due to the position of particles or the composition of that substance. So if it has bonds that are breakable, that is potential energy that is currently stored. If we are going to be applying heat to it, it has potential energy to change those reactants. Whereas with chemical energy, this is stored in the individual particles. So this tends to be associated with positions of electrons and nuclei. So if we're adding energy and the electrons are becoming excited, that is referring to the chemical energy of a substance. Or with nuclei, if you remember back to nuclear chemistry from Chem 1, those larger nuclei that could not hold themselves together would decay and give off these energy particles. That's a form of chemical energy. One thing that we're going to really harp on is the difference between temperature and heat. Remember, temperature is the measure of the kinetic energy of particles in a substance. If you look at the image, particles with a lower temperature are moving a lot slower. They don't have as much movement, so these tend to be solids at lower temperature. Whereas particles with more energy, moving faster, have a higher overall temperature. Whereas heat is the actual energy that is transferring from one object to another. And remember, the cause of heat change is that temperature difference. And remember, temperature is going to determine the direction of heat transfer. If two objects are the same temperature, there's not going to be a heat exchange. It's only when there's a difference between the two temperatures. And then you have to know, well, where's the heat going to flow? So heat is always going to flow from an object at a higher temperature into an object at a lower temperature. So take, for example, here we have boxes A and B. Box A is red, it's rather hot. Box B is cold, the blue one. Whenever the two come together, you are going to have heat go from the red box that is a higher temperature into the blue box that's a lower temperature. And that will happen until they are both the same temperature, which is where you end up with the purple boxes. This is the same thing if you're ever walking barefoot on, say, a tile floor. It seems really cold at first, but after you've been standing on it for a while, it doesn't feel as cold. That's where your body temperature is a lot warmer than the tile in your house. So your body is losing heat into the tile because of that temperature difference. After you've been standing there a while, it's not as cold because the bottom of your feet have reached the same temperature as that cold tile floor. It's kind of equalized. But remember, heat always flows from the higher temperature into the lower temperature. All right, so wondering how much heat an object contains. We already talked about it being based on temperature. The higher temperature will exchange heat with something that's a lower temperature. The amount of heat something has is also going to depend on its mass, and it's going to depend on its phase of matter. So we're kind of going to talk about those a little bit, of how those change over time. So if I gave you this picture and you have a pot of boiling water and then an iceberg, and I want to know which one has the higher temperature, you would obviously tell me that the pot of boiling water is a higher temperature than the iceberg. The boiling water is at least 100 degrees Celsius. The iceberg is frozen water, so it's most likely below 0 degrees Celsius. However, if I were to ask you which one contains more heat, this one's kind of hard. You have to look at how much of the substance there is. There are a lot more particles in the iceberg than there are in the pot of boiling water. So since there are more particles in the iceberg, it actually has more heat. This is a little bit tricky. It's just looking at which one has the bigger mass overall. If this concept is a little confusing, I want you to go to YouTube and check out the Eureka temperature versus heat video. It's a cute little cartoon. It goes through this difference a little bit more. So same thing, if you had a cup of boiling water or a swimming pool full of water that was regular temperature, the swimming pool full of water would have more heat, even though it is not the highest temperature, because there's more water particles in that swimming pool. Whenever we talk about thermochemistry and reactions, we kind of look at how heat is being exchanged. So in Chem 1, we talked about endothermic and exothermic, and we talked about the system and the surroundings. So the system is the material or process within which we're studying the energy changes. So where is the actual reaction occurring? Where is the actual energy change occurring? So say that we are doing a lab and we have a beaker on a hot plate and we are heating up a substance. That actual beaker where we are heating up the substance is our system. The surroundings is going to be everything else with which the system can exchange energy. So the hot plate is going to be part of the surroundings. The table it's sitting on is part of the surroundings. The air around the beaker would be part of the surroundings. And what we actually study is the exchange of energy between the system and the surroundings. So one of them is gaining heat, one of them is losing heat. So we kind of have to establish which is which. One thing to remember with thermochemistry is the law of conservation of energy. Remember, this still goes back with the law of conservation of matter. Energy cannot be created or destroyed. We're never making new energy. We're only taking it from one thing and transferring it into another thing. And when energy is transferred between objects or converted from one form to another, the total amount of energy that you have at the beginning is still the total amount of energy you have at the end. It may have just changed form. So I have a little diagram here. We have the beginning energy of the system was about halfway, and the beginning energy of the surroundings is about an eighth from being full. Whereas whenever they've made contact and exchanged heat, if you notice, the system energy is now about a fourth, and the surroundings energy is about 3/8. If you add those up, it's still the same total amount of energy, even though now the surroundings have more energy than the system. So no total energy was lost, it just went from one form into another. The law of conservation of energy goes back to the first law of thermodynamics. This is going to be our basis for a lot of our calorimetry calculations. So remember, the total amount of energy in the universe is constant. There's always the same amount of energy. It just goes from one type into another. This includes all kinetic and potential energies. It's not changing the amount of energy, it's just changing its form, changing what it looks like. So the change in energy in the total universe is 0. You're always going to have the same amount of energy. It's just you may now have more on the left side than the right side. So the change in energy of the universe is equal to 0. The change in energy of the universe, how you can find that, it's the change in energy of the system plus the change in energy of the surroundings. One of those should be a positive number. One of those should be a negative number. Depending on if it's an endothermic or exothermic reaction. But the amount of energy of both should be the same, so they're going to cancel out to be 0. So therefore, the energy, or the change in energy of the system, is going to be equal to the negative change in energy of the surroundings. This would be if it's an endothermic reaction. If the change in energy of the system is positive, the change in energy of the surroundings is negative, but it's going to be the same quantity, the same number. That would be reversed if it's an exothermic reaction, where the system, the energy in the system is losing energy, and the energy of the surroundings is gaining energy. But it's still going to be the same total amount of energy overall. They should cancel each other out. That last line is your basis for calorimetry. When you know exactly how much energy something has lost, you can figure out how much energy the actual system gained, and then we're going to use that to identify our substance and look at that overall. So I've kind of used these a couple times already from Chem 1. Remember, we talked about things being endothermic or exothermic. Remember, the prefix endo means in, so heat is going to flow into the system from the surroundings. So the system is gaining heat and the temperature is going up while the surroundings are cooling down. Whereas exothermic, remember, exo means out, so heat is flowing out of the system into the surroundings. So the system is losing heat and cooling down while the surroundings are heating up. One basis we're going to talk about with our thermochemistry are our states of matter. Those refer back to the kinetic molecular theory. This is referring to the amount of energy that the individual particles in a substance are having. It's also going to talk about the attraction between those particles. So the kinetic molecular theory is the state of matter depends on the kinetic energy of the particles and the strength of attraction between the particles. So depending on the temperature and the strength of attraction is going to result in your state of matter. And we're kind of going to walk through each state of matter so you can see what's happening with it. Gases have complete freedom of motion. If you remember, gases are very randomly moving. The particles are very fast. So they're complete freedom of motion. They can move out of a container. They can bounce off the walls of a container. And they actually have enough kinetic energy that overcome any attractive forces. Gas particles are not attracted to one another. So they're not necessarily going to stay in the container. If it's an open container, those gases are free to move around the room as they wish. So with gases, remember they're moving very fast, and there's enough energy that there's no attraction between those particles. Whereas on the flip side, with solids, remember solids are not moving. The particles are actually locked in place. So the particles are vibrating still because there's always going to be motion. So individual particles are vibrating in place, but they do not have enough energy to actually break those attractions. They are locked together. So remember, solids had like a definite volume and a definite shape. They're locked together. They're not going to expand. They're not going to change. Whereas the one in between, liquids. Remember, liquid particles are still moving. They can actually exchange places. That's where they have that limited freedom and they can move around. So they can move around in respect to the liquid itself, but the particles do not have enough kinetic energy to break those attractive forces. They're still attracted to one another. They're still going to cling together. So this is kind of similar to like if you're doing drops of water on a desk or on a penny. The drops of water kind of stick to one another. And that will happen with any liquid to a certain extent. But they'll actually make little puddles and the liquid particles will stick together versus spreading out all over the table. And remember, liquids, they have a definite volume, but they're going to end up taking the shape of their container, depending on what they're in. So looking at the states of matter and what happens when you add heat to it. So if you look across the top, we're adding energy from left to right. So the solids go from being locked together, vibrating in place. You add enough energy that it breaks some of the attractive forces to where the liquid particles are moving a lot faster. There's still an attraction between particles, but they're not completely stuck in place. Then you add even more heat, and it adds enough energy that it completely breaks those attractive forces so the particles can go where they wish. Whereas on the flip side, if you're cooling it down, if you have gas particles and you cool it down enough, they no longer have enough kinetic energy to keep those attractive forces at bay, so the particles become attracted to one another and condense into a liquid, and they're moving slower. You cool it down even more, take away even more heat, those attractive forces get really strong, the particles lock together, and they cannot separate, so it forms that solid again. It can kind of go back and forth across all of those. Heat capacity we talked about in Chem 1. In respects to, it's the quantity of heat required to, that should say raise, it's a little typo. So raise the temperature of the system by 1 degree Celsius. So this is talking about not the individual particle by 1 degree Celsius, but the whole object. So this is going to depend on the amount or composition of an object. So I know in Chem 1 I used the example, is water going to boil faster if you have a cup of water versus a swimming pool of water? The cup of water, there's not as much of it, so it's going to boil a lot faster than if you were trying to get that massive swimming pool to boil. The more of it you have, the more energy you need to raise the temperature. Whereas with composition, if you remember back from Chem 1, different substances have different specific heats. Some objects heat up faster than others. So if we have a pot of water that's boiling and we put a metal spoon in it and a wooden spoon in it, after a couple of minutes, if you try to grab that metal spoon, it's going to burn your hand. It heats up very quickly. Whereas if you try to grab that wooden spoon, it may be warm, but it does not heat up nearly as fast as that metal spoon does. So remember, this is what we refer to as specific heat. So specific heat is similar to heat capacity. It's specific heat capacity. But it's the amount of heat needed to raise the temperature of 1 gram of that object by 1 degree Celsius. So heat capacity referred to the entire object, whereas specific heat refers to 1 gram of that object. And remember, the lower the specific heat, the more its temperature rises when a given amount of energy is absorbed. So the lower the specific heat, the less energy it needs to heat up, so it heats up faster. So like, if you remember, our metals tend to have lower specific heat. Something metal is going to heat up a lot faster than water because it has a lower specific heat. If you remember, water has one of the highest specific heats. It's going to heat up slower than anything else. So looking at this picture, we have a pool surrounded by concrete. If you're in the pool, even though it's 90 degrees outside, it may not be 90 degrees inside the pool. That water takes a lot of energy to heat up. Whereas you step out onto that concrete, concrete has a lower specific heat. It heats up faster, so you're likely to burn your feet. So you have to look at those different objects heat up at different rates because of their difference of specific heats. Here's just a list of the vocab to kind of go through. Make sure that you're familiar with these terms, comfortable with them. We'll talk about them a little bit more in class, but we're going to use these as the basis for a lot of our calculations in the upcoming videos. If you have any questions about this, feel free to go back through this video. Check out that Eureka video for the difference between kind of the amount of heat of an object, and we'll use these later in class.